Can I start?
Yes, yes.
Okay. All right. Okay. Thank you very much for the invitation and the opportunity to present this work. So as I wrote down here, it's some ongoing work in collaboration with Kostas Kenderis, and so there are certain things that are clear, but I mean there are a lot of things that are also unclear. So I will we'll see as we go along. And let me also say, please interrupt me, during at any point during the talk. And I know, in the audience, there are people who have worked extensively on this topic. So especially Tassos, Petru, and Kostas Siampos. So if you want to comment on any of this part, so I will be glad. Okay. So let me just start with some very broad context. So what eventually we try to do here is just understand better time-dependent holography. And in particular, time-dependent holography is relevant both for understanding gravity and also for understanding strongly coupled quantum field theory. So we all know, for example, that there are out of equilibrium phenomena in gravity. So especially they have attracted a lot of interest in recent years because of gravitational waves. So for example, black hole mergers are examples of some such phenomena in gravity. But also we know very well, from very detailed studies, in holography, that non-equilibrium phenomena in quantum field theory can be, such as heavy ion scattering, can be described also very successfully through gravity. So time-dependent phenomena are in general not easy to understand. And for example, they are not amenable to perturbative techniques usually. So that's why we need, for example, the gauge gravity duality that relates out of equilibrium physics in gravity to the strong coupling of quantum field theory in order to study such phenomena. So black holes play a very key role in all this, and especially because they are some important playground for understanding quantum gravity on one side, and also they correspond to thermal states in the dual quantum field theory through the standard ADS-CFT dictionary. And in particular now, when we have time-dependent phenomena, they correspond also to time-dependent phenomena on the gravity side. They correspond also to time-dependent phenomena on the field theory side. So, for example, black hole formation here corresponds to thermalization in the dual field theory, and also near equilibrium physics on both sides is also related. So, for example, on one side we have hydrodynamics on the field theory side, and on the gravity side, this can be related to some kind of derivative expansion around a black hole solution. Now, what we are interested here in this work is going beyond this kind of near equilibrium physics, so really time-dependent solutions that are usually only accessible numerically. So, and one exception to this rule, so one very special case of solutions that we know analytically is the so-called Robinson-Trautman class of solutions of general relativity. So this allows us to study non-perturbative non-equilibrium physics, but in analytically. So in that respect, it's a rather valuable class of solutions that allows us to get insight into the non-equilibrium phenomena, both in gravity and field theory. Now, the standard Robinson-Trautman ADS solutions. So let me just say first that actually the Robinson-Trautman solutions, they exist. They are solutions of Einstein's equations, and they exist for any value of the cosmological constant. So there are asymptotically flat versions and asymptotically ADS. And but I'm going to focus here on the asymptotically ADS ones because we want to study holography also in that context. So the standard Robinson-Trautman ADS solutions approach the ADS Schwarzschild black holes at late times, and as such, they provide a model for gravitational collapse and thermalization. However, another important feature that these solutions have, which is also partly why we're interested in these solutions, is that they are not compatible with the standard Dirichlet boundary conditions. So as I will review a little bit later, the holographic dictionary depends not just on the solution of Einstein's equations or the bulk equations, but also on the boundary conditions that we impose on these solutions. And the standard dictionary imposes the so-called Dirichlet boundary conditions that keeps let's say the boundary metric, for example, fixed. And if we impose these boundary conditions, then the standard holographic dictionary applies. So I will review this a little bit later, but the important point here is that the Robinson-Trautman class of solutions is actually not compatible with Dirichlet boundary conditions, so which presents a puzzle, but also a challenge, to try to understand the correct boundary conditions and the corresponding holographic dictionary. So as a way, so besides understanding the correct boundary conditions for the Robinson-Trautman class of solutions, one of the goals of this work is also to try to generalize this class of solutions in order to find solutions that are compatible with the Dirichlet boundary conditions. So the outline of my talk is the following. So I'm going to start with just reminding you some facts about the Robinson-Trautman ADS solutions. Then I will make some kind of a digression into the so-called accelerated black holes and the connection they have with Robinson-Trautman solutions. Then I'm going to come back to the question of Robinson-Trautman holography and the issue of the boundary conditions. And finally, I conclude here with some ongoing work about generalizing these solutions. Okay, so as I mentioned, the Robinson-Trautman ADS solutions are solutions of Einstein's pure Einstein gravity, Einstein-Hilbert gravity with a negative cosmological constant. And the line element can be written in this form here. So the important thing is that it contains two functions here. So there is this conformal factor here and this function f here, but the function f is actually determined in terms of this conformal factor here. So if you solve Einstein's equations, you find that this f here is expressed in this way, where delta stands here for the Laplace-Beltrami operator, the Laplacian, if you want, on the Riemann surface sigma. And moreover, this function phi is not completely arbitrary, so it has to satisfy a fourth-order differential equation, this one down here, which is known as the Robinson-Trautman equation. So, and let me also point out that there is this mass parameter m here appearing in the solution. So now we can actually, to get some insight into the solution, we can compute, for example, some curvature invariance. So one of the curvature invariance that we can compute is the Weil square. So when this mass parameter is not equal to 0, then we see that the solution has a curvature singularity at r equal to 0, because the Weil square goes in this way. And moreover, in that case, we also have a non-trivial Robinson-Trautman equation. So remember, the Robinson-Trautman equation also depends on this mass parameter here. So in that case, it gets this extra term when the mass is non-zero. And this equation here, the Robinson-Trautman equation, in this case, is a special case of what is known as a Calabi flow, which in general is applicable for Kähler manifolds. And so it has certain properties that have been established, like, in general. So for example, here, the Kähler volume and the integrate curvature are preserved along such a flow. And the integrate curvature square here is actually monotonically decreasing along the Calabi flow. And in that sense, like, this acts like kind of some kind of central function, like, like the C theorem, for example, in RG flows. Now, so there is this Calabi flow, like, in time, that appears like in the Robinson-Trautman solutions, and then one can ask what happens like at late times, which corresponds essentially like to the fixed point. And this depends actually on the topology and the smoothness properties of the base manifold, this Riemann surface. And it has been established that, for example, when sigma is topologically a two-sphere and also has some Christian smoothness conditions, then the fixed point of the Calabi flow is actually the constant curvature metric on S2, which corresponds to this function phi here, the conformal factor taking this particular form here. So once we insert this form of the conformal factor back in the Robinson-Trautman solution, then we recover nothing but the ADS Schwarzschild black hole in so-called Eddington-Finkelstein coordinates. So we see that at late times, the Robinson-Trautman solutions, like, provided there are some assumptions on the base manifold, it always flows to the ADS Schwarzschild solution. So now, putting aside for a moment the Robinson-Trautman solutions, we can start from the ADS Schwarzschild solution and look at perturbations, like linear perturbations around the Schwarzschild solution. So this has been studied a long time ago, for example, by Regge and Wheeler. And they found that one can formulate the problem like in terms of an effective Schrödinger Hamiltonian. Actually, there are two Schrödinger Hamiltonians. So the problem can be formulated in this way, where epsilon is some energy levels, and the Hamiltonian takes this form here. So this W plays the role of some kind of superpotential in quotes. So the expression is related here, is given here. And this R star here is the so-called tortoise radial coordinate. So, and the plus or minus corresponds like to parity even or parity odd fluctuations. So now this is true like for any linear perturbations around the Schwarzschild black hole. But then there are particular, so this system actually admits fake supersymmetric structure in the sense that we can write the Hamiltonian like in a apparently supersymmetric way. So if we introduce these operators here, we can write the Hamiltonian, we have then these two Hamiltonians, H plus and H minus, that can be expressed as in terms of these ladder operators. And then we can write the total Hamiltonian in this way, in terms of these two matrix operators in this way. So the anticommutator of these two operators gives back the Hamiltonian. So there is this kind of SUSY algebra that appears, although there was no actual supersymmetry like in this system. Nevertheless, this apparent supersymmetry allows us to identify some special fluctuations. And these are the so-called algebraically special modes, which corresponds to modes that are annihilated by this operator Q. So they satisfy this equation here. So it's a first order equation in the radial coordinate, as opposed to the second order equations that generic modes satisfy. And they correspond to zero energy or these frequencies are given by these particular expressions here. So these are like the so-called, again, algebraically special modes. So they were first identified by Sandra Sekar. And they have the property that they vanish. So this amplitude here vanishes on the wave on the horizon. And actually at infinity is non-vanishing, and it satisfies. So this shows that this mode satisfies some kind of mixed boundary conditions. So again, not Dirichlet boundary conditions, and we'll come back to this point a little bit later. So this was, again, studying linear perturbations of the ADS-Schwarzschild solution. So a priori unrelated to the Robinson-Trautman solution. On the other hand, we saw earlier that the Robinson-Trautman solution arises as, the ADS-Schwarzschild solution arises as the late time limit fixed point of the Robinson-Trautman solutions. But now we can do something slightly different. So we can start from the fixed point of the Robinson-Trautman solutions, which is ADS-Schwarzschild, and look for perturbations within the Robinson-Trautman class of solutions. So this means that we are looking at perturbative solutions of the Robinson-Trautman equation around the ADS-Schwarzschild solution. And what one finds is that in this case, the solutions, the perturbations take this particular form here, and where the frequencies and the amplitudes are of this form. And this can be identified exactly again with the algebraically special modes of the Schwarzschild black hole. So in other words, so what we conclude from this analysis is that the Robinson-Trautman solution, at least in the case of the topologically S2 with sufficient smoothness assumptions, corresponds to the nonlinear description of the algebraically special modes of the Schwarzschild black hole. So it provides a nonlinear, it's an exact solution that describes the dynamics of the algebraically special modes. So, as I said earlier, so both the linear fluctuations and also the full nonlinear Robinson-Trautman solution does not satisfy Dirichlet boundary conditions at the conformal boundary of ADS space. And one indication of this is one indication we already saw is namely the fact that this is at the linearized level, these modes vanish at the horizon and they are non-zero at infinity. But another one is that actually these modes, they modify the boundary metric, which is usually not the case like for solutions that satisfy Dirichlet boundary conditions. And then another indication is that actually the boundary metric of the Robinson-Trautman solution actually depends on this mass parameter of the solution. And again, that is another indication that these solutions do not satisfy Dirichlet boundary conditions. So then there are several questions that arise. So two of them is what are the correct boundary conditions compatible with these algebraically special modes? And if there is a generalization of the Robinson-Trautman solutions that describes the non-algebraically special modes. So is there any question regarding this part? So before we move on now to accelerated black holes.
Yanni. Yeah, so just to understand a little bit. So the Dirichlet boundary conditions is, of course, to fix the conformal class of the boundary metric. Okay, so we know that, well, the boundary metric of Robinson-Trautman is not conformally flat.
Correct.
So if I wanted, well, just to give an example, if I wanted to start from a Schwarzschild ADS and produce Kerr ADS by fluctuating around Schwarzschild ADS. Then I suppose, because Kerr ADS has an asymptotically conformally flat metric, then you would say that the Dirichlet boundary conditions apply, because still the metric will stay in the conformal flat class.
Mm-hmm.
But now, if I want to produce a metric like Robinson-Trautman, which is not asymptotically locally, well, whose boundary metric is not actually conformally flat,
Mm-hmm.
then necessarily I need to change my boundary class of metrics. Is that the general statement? So this is a general statement for metrics that are not conformally flat in the boundary. So that is what I'm trying to understand.
Well, I'm not sure the conformal flatness of the boundary, is not particularly important, I think, in this at this point yet, because there are examples of like solutions that satisfy Dirichlet boundary conditions, but nevertheless the boundary metric is not conformally flat, right?
Yeah. So this is what I'm trying to understand. How, because you said that they don't satisfy boundary conditions because they change the boundary metric or the conformal class of the boundary metrics. What?
Yeah. So what I meant by this, I will come back to this later. It's also related to your earlier work, but what I meant is that the boundary metric here, as I will show a little bit later, it actually depends on this mass parameter, right? Which is usually not the case for like standard solutions that satisfy Dirichlet boundary conditions. So if you just perturb the mass, for example, like in the Schwarzschild black hole, right? You don't change the boundary metric.
Sure.
So, but in this case, you do, right? In the general Robinson-Trautman class, if you change the mass parameter, you actually change the boundary metric.
Yes. So it's similar with the Kerr. If you change the A, the rotation parameter, you change the Kerr boundary metric. But you stay
sure, but it's not exactly the same. It's not exactly the same because, like in that case, it is known, right? The Kerr, if you change this parameter A in the Kerr, you can actually compensate that by a diffeomorphism plus a Weyl transformation.
Okay.
That is not the case here for the Robinson-Trautman. You cannot compensate by a diffeomorphism and Weyl transformation.
No, okay, I agree with it. I think that the difference is that in the Kerr case, you stay in the conformal class of conformally flat, but here you move away from the conformally flat class by making this. So that I think, yeah, that's the point I wanted to make, but I want to see what you say afterwards. Yeah.
Yeah,
but it's up to discussion. I agree that it changes the Dirichlet boundary conditions, I would say. I think it's interesting to understand why in this case and not in other cases. I guess you will say about that.
Yeah, let me move on and maybe we can come back to it at the end.
Sure. Thanks.
Yeah, sure.
Yannick, can I ask you something?
Of course.
Can you tell me the isometry of these Robinson-Trautman spaces? Because maybe you can understand the lack of ADS or whatever.
There are no isometries for the generic Robinson-Trautman. There are no isometries.
Then why you expect the CFT then? There is no isometries? Or a boundary or whatever?
So the boundary is asymptotically locally anti-de Sitter, right? That doesn't require any isometries, right? So so a generic asymptotically locally anti-de Sitter space, doesn't have any isometries.
Yes, but you don't expect, that you have something, the usual rule that there is the global symmetries of the boundaries, isometry on the bulk, something like that. Do not work here?
Sure. No, that applies, right? But it's the equivalent of putting like a CFT, let's say, right? On a curved manifold. So we'll see later, right? And also I will review that.
Good. Okay.
Right? But if you put a CFT on a generic manifold, of course, it's not guaranteed that you're going to have any isometries.
No, but you expect to have asymmetry, otherwise it will not be a CFT, you have a CFT, you have a symmetry, otherwise it's a free theory. It's not a CFT.
comment on that.
Sure, Tasso, go on.
Maybe you can go on because I think it will take.
No, man, just a comment. I think this is an important point which is not well appreciated in general. I think, in my opinion, actually, what you have in the boundary is a vial theory. It's a theory that lives on a metric that it doesn't have to have any isometries, but the theory has vial invariance because you can rescale this metric, which has no isometries, maybe. You can rescale with an arbitrary vial factor. This is what basically this is what ADS-CFT gives you in general. I think it's not a CFT; it's a vial theory.
So you only have a vial invariance, you mean?
You have vial invariance. The question is whether.
But if it's a local theory, then why should not have full conformal invariance if it's vial invariant?
Well, that's I think that's $1 million question. I think, yeah, okay.
Well, I don't quite agree in general because, like, I mean, even in general, right? I mean, also like in odd-dimensional bulk, right? The even-dimensional boundary, in principle, I mean, you don't even have vial invariance if there is an anomaly, a conformal anomaly.
Yes, that's
so
true.
Sure, that's it. Yeah,
that's true.
We have vial invariance up to anomalies. Yeah.
But in any case, I mean, the same way that you can put n equal 4 super Yang-Mills on a sphere or, like, I mean, any curved manifold, right? I mean, in that sense, I mean, it's a CFT. It's not a CFT in the sense that, I mean, the vacuum preserves conformal symmetry, but nevertheless, as a theory, you can put it on a curved manifold.
Yeah, no, this I agree. Okay. Let's
but,
go on.
but excuse me, but the rotating curve has conformal symmetry.
Yeah,
the rotating curve, that's right, yes.
So, in a sense, either there is no continuous limit to the Schwarzschild, or also the Schwarzschild limit would have some sort of conformal symmetry, I guess.
Yeah,
Am
of
I
course,
right?
Schwarzschild does,
Yeah.
right? I mean, so the Schwarzschild, right? I mean, it corresponds to the late time behavior of the Robinson-Trautman. So
That's right.
At the late times, right? I mean, conformal symmetry emerges.
Yeah.
Okay.
No, I just intervened in the sense that there was a statement that there is no conformal symmetry. There must be something.
Sure.
So, Nico,
Yeah.
the rotating hair has conformal symmetry because the boundary metric is conformally flat.
That's right.
So all the isometries of the flat metric, all the conformal isometries, are the isometries of any conformal flat metric. But in generic case, if you go away from a conformally flat boundary, and that was
sorry. In generic, I agree, but there are cases where the conformal symmetry. That was my point. It's fine.
Yeah. Of course. In all conformally flat manifolds.
If you break the conformal symmetry by
99%.
boundary conditions, of course, then you don't expect it to be valid.
Yeah.
Thank you. Thank you, Ioannis. Thank you, Tassos and Lekos.
Okay, so maybe I continue, and then, I mean, if there are more questions.
May I?
Sorry, was there something?
Yeah. It's Kostas.
Costa, yes.
I asked one question back in the previous slide.
Yes.
So, related to that, to the fact that you don't have Dirichlet boundary conditions, could I think also an analog case like the Taub-Nat case, where my boundary, it's related also to Tassos' question, where my boundary is not conformally flat, and it's locally asymptotically ADS, and again, the boundary metric depends on the Nat charge.
No, I mean, that is different case, right? I mean, I would classify the type Nat solution as being, I mean, compatible with Dirichlet boundary conditions, right? The Nat charge is a topological charge, right? I mean, so it's a property also of the boundary. So, and there is nothing that, I mean, okay, it's not conformally flat, but I mean, this doesn't necessarily mean that, I mean, it's not compatible with Dirichlet boundary conditions.
Okay.
So Taub-Nat, I mean, I would say, I mean, it's compatible with Dirichlet boundary conditions. It's not, I mean, it's not in the same sense that I'm talking about here.
Okay, Yanni. Okay, thanks.
Sure. Okay, so now let's make a digression, like a little bit into accelerating black holes. So a priori, that is like something slightly different type of solution. So again, there are different versions of these accelerating black holes, like depending on the value of the cosmological constant. So here again, I'm focusing on the asymptotically ADS ones. And just in case you're familiar with them, sometimes these are also known as the symmetric or Klebansky-Damiansky solutions. So they all refer like to the same type of solutions. And these are again solutions of the vacuum Einstein equations with a negative cosmological constant in this case. And they take this particular form here. And now these three functions, so they are parameterized again they depend on two parameters, so mu here and alpha. And roughly speaking, this correspond to respectively to mass. So this mu corresponds roughly to a mass parameter, and then alpha corresponds roughly like to acceleration. Okay, so this is like just the solutions, and one of the reasons why one might be interested in these solutions is, again, recently there have been discussions of the thermodynamics of these solutions, and this presents several subtleties. So one would like to understand better, for example, the thermodynamics of these solutions. Now, again, for when this new parameter is not equal to 0, the solution has a curvature singularity. So in this case, in this coordinates corresponds to rho going to infinity. And then when this product of the two parameters is non-zero, then it actually has some kind of conical deficit. So in that case, it is impossible to choose the period of this azimuthal angle phi, so that this constant rho and t surfaces are smooth and smooth as 2. So in this conical deficit, you can parameterize in various ways. So one way that is kind of standard and convenient is like to just take these two angles, like so the north and the south pole, and in that case we define this this value of this function p that appears here, like for these particular angles we call them p plus and minus, and then it's consistent to choose the period, for example, of phi, like to be this expression here, where n plus and n minus are integers, positive integers. So and then in that case, we have conical deficits at the north and the south pole. So it's actually possible also to move the conical deficit at one of the two poles, and then the other one being smooth. But this symmetric way is kind of more convenient usually. And then this is also related to some other part of the literature that has appeared, especially in the context of supersymmetry. So in the special case where these two integers are co-prime, then this is known as a spindle. So just a cartoon here of this constant RT surface here is that you have like this kind of conical deficits here at the north and the south poles. Now, one interesting observation, which I think, it was previously known, at least in some cases, I've seen it, for example, in the case of asymptotically flat accelerating black holes, like in the context of the symmetric, that it arises as a special case of Robinson-Trautman solutions, but I hadn't seen that in a more general, as a more general setting. And we showed here that actually you can always write the accelerating black holes as a Robinson-Trautman solution. So, and here is the coordinate transformation. So there's this on the left-hand side here are the Robinson-Trautman coordinates, and on the right-hand side here are the coordinates that appear in the accelerated black holes. And this function here of theta is actually a rather complicated function that can be expressed in this way here in general. And then this Weil factor that appears on the base of the Robinson-Trautman solutions can be expressed in this particular way here. So now, given the time, I'm not probably going to go into the detailed discussion of the map between the Robinson-Trautman and the accelerating black holes. But the point is that essentially now you can, by analyzing this map of coordinates here, you can show that these accelerating black holes can be thought of as a pulse essentially that starts from one pole of the S2 and then arrives at the other pole of the S2. And then here is if I plot it it's best seen here in logarithmic coordinates. So I plot here this conformal factor of the projective S2 that appears in the Robinson-Trautman solution versus this this kind of radial distance, like on the projective z-plane in of the S2, and then you see here that you have a pulse that goes like from one pole. So the north pole corresponds to this point, and the south pole corresponds to this point here. Okay, so this is not particularly important for the rest of the discussion. I just want to point out that all the accelerating black holes can be actually understood as special cases of Robinson-Trautman solutions. And then there is here some classification, the so-called Petrov type. So the Petrov classification of the solutions, depending on the components of the bulk tensor of the bulk solution. And in this case, this symmetric, in other words, the accelerating black holes are what is known as Petrov type D solutions. Now, another important point that I should point out is that this symmetric or the accelerating black holes, they are also fixed points of the Calabi flow. So remember that, like, whenever we have a Robinson-Trautman solution, we have a Calabi flow. But there was this proof earlier that the fixed point of the Calabi flow, if we assume that the base Riemann surface is topologically S2 and has sufficiently smooth metric, then in that case, the fixed point is always like the round, the Ricci constant two-sphere. However, here, because we have this conical deficit, so this kind of violates the assumptions of that theorem. And in this case, there's another theorem that applies, which was proven by this gentleman here. And then it shows that in this case, so for axisymmetric base manifolds, so this does apply to the accelerating black holes because of these conical deficits that break the symmetry like to axisymmetric symmetry. So in that case, the fixed point of any solution is actually, so this symmetric arises as the fixed point of any solution, any Robinson-Trautman solution with axisymmetry. Okay, so now let me move on back to a more general discussion of the Robinson-Trautman solutions. And now I will step back a little bit and discuss general asymptotically locally anti-de Sitter manifolds. Of course, the Robinson-Trautman solutions are particular subclass of this. So, and let me remind you that we can always write the solution. So here we're like in 4 dimensions. So there are solutions like Robinson-Trautman solutions like in different dimensions, but for various technical reasons, we focus on 4 dimensions. So, and we can always choose a gauge where the metric takes this particular form. The radial coordinate here, the conformal boundary of asymptotically locally ADS space here corresponds to rho equals 0. And this metric here in the transverse space admits an expansion in this radial coordinate of this canonical form. And here I put in red the 2 functions that are a priori undetermined. So G0 is completely undetermined here and is interpreted holographically as the boundary metric. Whereas this function G3 here is almost arbitrary, except that it satisfies 2 constraints. So if I parameterize it judiciously in this way here, so I just define Tij to be this G3, then in this case we have that Einstein's equations require that this Tij is traceless and also is covariantly constant with respect to this boundary metric G0. So this suggests like that actually we have a conformal field theory in the sense that these are the word dentists for a conformal field theory like in 3 dimensions. So there are no conformal anomalies in this case, so that's why you have 0 here. Now for Dirichlet boundary conditions, this is the standard dictionary, but of course, like if now we don't have Dirichlet boundary conditions, this dictionary needs to be revisited. Now we can apply this expansion, so this general expansion that applies for any asymptotically locally ADS manifold, we can specialize it now to the Robinson-Trautman case. And in this case, we find that the boundary metric takes a particular form. So again, it's just, there is this conformal factor, like multiplying these base coordinates. And there is also this time-like coordinate, of course. And then again, now this Weyl factor satisfies the boundary version of the Robinson-Trautman equation. So these hats here are not particularly important, but technically they correspond to the transverse coordinates, but they are not exactly the same as the ones in the bulk Robinson-Trautman solution. There needs to be some bulk diffeomorphism that relates these coordinates to the transverse coordinates in the Robinson-Trautman. That's why they are not exactly the same. Okay, but this is the structure of the boundary metric now for Robinson-Trautman solutions. And again, here we see the reason why I say that they don't satisfy Dirichlet boundary conditions, namely that the boundary metric depends on the mass parameter of the solution through this Robinson-Trautman equation. So if I change the mass parameter, it would affect the solution of this Robinson-Trautman equation that determines the boundary metric here. So this is not the standard thing that happens like when we have a solution that's compatible with Dirichlet boundary conditions. Now, as Tansos mentioned earlier, so of course, this boundary metric is not conformally flat. And this you can see now in 3 dimensions. So the boundary is 3-dimensional. So when we are in 3 dimensions, remember that the conformal flatness is decided by the cotton tensor or the cotton York tensor instead of the Weyl tensor. So, and in this case, we can simply compute it using this boundary metric here. And what we find, so we'll show explicitly the form of this cotton York tensor in a moment. But the important thing here is that it's not 0 generically, which means that the boundary metric is not conformally flat. So, and we can also compute the holographic stress tensor. So, and here I give all the components. So you see that there are 2 components, the TT component and the ZZ bar component that depend on this mass parameter. And all the other components are local functions of this Weyl factor. So in total, we see that the stress tensor depends locally here on the boundary metric. And this is something that is rather surprising because normally when we, so the stress tensor is actually a non-local function of the boundary metric for general asymptotically locally ADS manifolds. And this is why we get all these dynamics, right? And so the stress tensor should be viewed as the 1-point function of the stress tensor in a dual conformal field theory, and then taking functional derivatives of this 1-point function with respect to the boundary metric produces non-local correlation functions. So the fact that here we have a local relation is a manifestation, again, that something very special is going on with the solution. And of course, we know that this reflects here the fact that we have an algebraically special solution. So now in particular, we can compute again the components of the cotton tensor, as I mentioned earlier. So just from the expression that I gave above, but now we can relate them to the expressions for the stress tensor, for the components of the stress tensor. So we see here that, well, some components are 0, but the rest of the components are actually related linearly to certain components of the stress tensor. So here we have something rather unusual, namely we have a local functional of the boundary metric, the cotton tensor, being related to something that is usually an operator, and it should be a non-local function of the boundary metric. So these relations appear here. So here there are like a number of comments that I should make. So first of all, this is again reminiscent of what happens in the case of mixed boundary conditions, for example, when we have scalars. So this is probably the most familiar example when mixed boundary conditions arise in the context of the ADS-CFT correspondence. So in that case, remember that we have like 2 modes in the asymptotic expansion of the scalars. And for solutions that satisfy mixed boundary conditions, these 2 modes are actually related in a particular way. It could be linear or it could be non-linear for multi-trace boundary conditions. But again, there is a particular relation between the modes. And then this is very reminiscent of what happens for those scalars. Then another comment here I should make is that actually there is no covariant way of writing these relations here. And this is in contrast to something very similar that appears like in an aerial work of Tassos Petku, where they had again some non-Dirichlet boundary conditions like for ADS gravity in 4 dimensions. But in that case, the cotton tensor again was related linearly to the stress tensor, but in a covariant way. So there are such mixed boundary conditions that you can impose, but for some reason, this is not what these are not exactly the boundary conditions that the Robinson-Trautman solution satisfy. However, there is a way of writing a little bit more compactly the relation between the cotton tensor and the stress tensor, and this was kind of hinted at in work by this gentleman here from 2014, where you utilize this time-like one form that appears like in the boundary metric of Robinson-Trautman solutions. So in this case, if you we can write this stress tensor in this way, like we can split it into 2 parts. Here is like the perfect conformal fluid part, where P0 is related to this mass parameter of the Robinson-Trautman solution. And then this Z tensor here is actually related locally to the metric through this cotton tensor C here. So now what appears here to be important is this one form, this time-like one form here, that actually defines mathematically what is known as an almost contact structure. So it seems that this plays some important role in understanding like the boundary conditions that arise like in the Robinson-Trautman class of solutions. Okay, so now let me finally move to the last main part of the talk. So now we're trying to understand like both the boundary conditions that Robinson-Trautman solutions satisfy, but also try to go beyond the Robinson-Trautman class of solutions in order to find solutions that are not algebraically special and therefore can satisfy Dirichlet boundary conditions. So now the strategy that we're following here is the following. So as we saw earlier, so the stress tensor that corresponds to Robinson-Trautman geometries is related algebraically to the cotton York tensor, and that reflects the fact that we have algebraically special solutions. So this is a particular, so if you want the holographic stress tensor correspond to Robinson-Trautman solutions is a very special case, a very special solution of the holographic world dentist here that we saw earlier for generic asymptotically locally anti-Sitter spaces. However, one could try to go beyond Robinson-Trautman solutions by finding more general solutions to this conformal world dentist. So that's one question that we try to raise. So are there more general solutions that we can identify of these equations? And if yes, then the second question that arises is how can we reconstruct the bulk solutions like corresponding to these more general solutions of the world dentist? Of course, the solution that corresponds to the Robinson-Trautman equation, we know how to reconstruct the bulk metric because we know already the Robinson-Trautman solutions. The question is how we would, if and how would we able to go beyond that for non-algebraically special solutions. Okay, so now again to actually try to address these questions, we utilize again this almost contact structure. So we look at the boundary metric of generic form of this generic form here. So again, we have like this time like one form that corresponds to the almost contact structure, and then we decompose everything. So we can decompose the stress tensor relative to this almost contact structure, and then the world dentist reduced like the corresponding world dentist for this operator. So now with respect to that, we have like 3 operators. We have a 2-dimensional stress tensor, we have a two-dimensional U1 current, and we have also a scalar operator. And the word dentist that I wrote before, so the holographic word dentist for the three-dimensional stress tensor, they take this form here. So where K here is just this extrinsic curvature of the boundary metric. Now, it turns out that we can actually find more general solutions of these word dentists, and in fact, we can find exact more general solutions of these word dentists than the ones corresponding to the Robinson-Trautman class of solutions. So in particular, one, well, it's still infinite generalization of the stress tensor of the Robinson-Trautman solution is the following. So we have here this expression here for the scalar operator, so it depends on this mass parameter, so it's just a constant. But then the U1 current and the stress tensor are expressed in terms of this scalar field phi. So this tau here is this Liouville stress tensor for the field phi. And then you can show that these expressions here satisfy the word dentist that I wrote before here, provided this scalar phi satisfies the Liouville equation on this boundary metric. So this is the Liouville equation here. So in terms of this Ricci scalar. So the Ricci scalar of the two-dimensional base is just given in terms of the Laplacian of this Weil factor phi. So this is just the Liouville equation for phi, small phi. And of course, besides that, we also need that this capital phi, so the Weil factor satisfies this Robinson-Trautman equation. Now, the important difference here is that the solution here satisfies the word dentist, but for any field phi that satisfies the Liouville equation. So it doesn't have to be that phi is equal to phi. This is actually the case that corresponds to the Robinson-Trautman solutions. So if we take the Liouville field to be equal to the Weil factor, then we just recover the Robinson-Trautman solutions. However, any Liouville field phi is also a solution of the, leads also to a solution of the word dentist. So this is like an infinite generalization to the class of Robinson-Trautman solutions, at least at the level of the word dentist, of the holographic word dentist. So this is reminiscent, maybe for those that are familiar with that, this is reminiscent of the fact that the word dentist for a two-dimensional CFT, so namely the trace condition and the divergence of the stress tensor, can be solved in general by a Liouville stress tensor that has the appropriate central charge. So this is something analogous, but now we have like a 3+2, so we have a three-dimensional, like 2+1 dimensional boundary. And then another comment is that actually there are even more general solutions of this word dentist that I'm not discussing here. And there are interesting connections like with the so-called celestial holography that has been discussed in recent years, like the null infinity of asymptotically flat spaces. So here again, there can be some parallels. One can draw some parallels to that analysis here. Okay, so now this was again the solution of the word dentist, but as I said, the next step is that we would like to find the corresponding bulk solutions. So the solution of the word dentist, of the holographic word dentist, already gives us some non-trivial information. So for example, it gives us some, sorry, was there a question? Okay, so the solution of the word dentist does give us some non-trivial information. So in particular, on the boundary conditions that the solution satisfy, and also like the symmetries that are compatible, like with the solutions. But nevertheless, we still need to reconstruct the bulk solution if we want to address questions such as, for example, regularity of the solutions. So the next stage then is now to discuss how we can actually try to reconstruct the bulk geometries. And the approach we are following here is we try, first of all, like to go to choose a gauge for the bulk geometry that is compatible with the presence of this almost contact structure. So, and in that respect, I mean, we chose this particular gauge here. So this is a gauge that like in the same sense that the Pfefferman-Graham gauge is a particular gauge for any four-dimensional solution. So here we have another gauge choice that is more like Bondi-like, but is not exactly Bondi gauge, but is kind of closely related to Bondi gauge. Right, but Bondi gauge is not compatible, like with the presence of this almost contact structure. So that's why we choose this particular gauge here. So and then now we can rewrite the full set of four-dimensional Einstein equations in terms of equations for this two-dimensional metric, two-dimensional vector field, and two-dimensional scalar. When I say two-dimensional here is that they are, I treat them as functions on the base manifold here, but they actually depend on all four coordinates. So they depend on R, U, and also the base coordinates. So there's no, so the solutions are, the equations are completely equivalent with the four-dimensional equations. It's not a dimensional reduction. And so one important aspect of this parametrization here of these gates is that the abelian, so this vector field A corresponds like to an abelian gauge field on the two-dimensional base if we do this kind of transformations that depend only on the base coordinates. So this this transformation here is a symmetry of this gauge. Now, the Robinson-Trautman solutions, they can be also very nicely accommodated in this particular gauge because of the following two facts. So first of all, one can show that setting A equal to 0 is a consistent truncation of the equations of motion. And moreover, the Robinson-Trautman family arises in the following way. So if we consistently truncate the theory to the A equals 0 sector, and then we also focus on conformally flat two-dimensional metric, then one can show that the solution is necessarily Robinson-Trautman. So when I say conformally flat, I just mean that the two-dimensional metric takes this form where chi here is some Weil factor. So one can prove that if any solution of the four-dimensional equations of motion that has A equal to 0 and the two-dimensional metric is of this form, then it's necessarily Robinson-Trautman. And here I should comment also that in general, like in two dimensions, one could say that any two-dimensional metric is conformally flat. However, this is not exactly the case in this case because we have fixed already this Bondi-like gates in 4 dimensions. So if I do here, so remember that this Weil factor here depends also on the extra coordinates, so R and T, R and U. So if I do a two-dimensional diffeomorphism on the base manifold here, in general, I will go outside of these Bondi-like gates in 4 dimensions. So the statement here that the two-dimensional metric is conformally flat is actually a dynamical statement within these gates. It's not a matter of taking a gates in 2 dimensions. Okay, so I think I'm almost out of time, but I'm also almost done. So now, regarding the work still in progress, is how we would actually go beyond this Robinson-Trautman class of solution that corresponds to A equals 0 and conformally flat two-dimensional metric. And in order to do that, we are first of all trying to go beyond by studying linear perturbation around Robinson-Trautman solutions. So this could this gives us like 2 different kind of insights. First of all, it will allow us to find the bulk reconstruction of the generalizations, the more general solutions of the Robinson-Trautman world entities, at least to linear level. But also, it will allow us to compute like holographic 2-point functions around general Robinson-Trautman solutions. And that, again, allows us to study the boundary conditions that these solutions are compatible with. And then, rather more optimistically, or a more ambitious plan is like, once you have the linear solutions, like to try to go beyond, like to try to reconstruct the bulk solution beyond linear order at least for some particular solutions of the word entity, like for example, the one that corresponds to this Louisville field that I mentioned earlier. Okay, so let me summarize. So first of all, the Robinson-Trautman class of solutions is valuable because it provides a window into time-dependent non-equilibrium phenomena, and both in gravity and holography and quantum field theory via holography. And it corresponds to a nonlinear description of the algebraically spatial perturbations around a black hole, like the ADS Schwarzschild black hole in particular. It includes, so Robinson-Trautman, the Robinson-Trautman class of solution includes accelerating black holes as a special case. So by understanding holography and thermodynamics for the Robinson-Trautman class of solutions, it also helps understand the subtleties related to accelerating black holes. And again, there is no proper holographic understanding yet of this of the holographic dictionary and the boundary conditions related to the Robinson-Trautman solutions, and in particular the Robinson-Trautman anti-de Sitter solutions. And one of the key ingredients that seem helpful in understanding the properties of Robinson-Trautman solutions is the presence of this almost contact structure that appears at the conformal boundary of Robinson-Trautman ADS solutions. Thank you for your attention.
Thank you very much, Ioannis. So let me stop the recording now. And